Alright, hell yeah. So this video is about problem solving. And this is not a complete solution, but this is just kind of a taste of an aha moment. So my brother gave me a physics book with riddles, and this is going to be, you have a cube with an ant at point A, and the ant can walk along any surface, but what's the shortest distance to point B? And things like these are riddles because, you know, you haven't done any problems prior to it. You don't have a textbook that says, hey, here's, you know, some scenarios that you're going to be using, and then you're going to apply it to this problem. So you're kind of just left with, I don't know, critical thinking, thinking outside the box, making a easier problem, taking things to the extreme. And then so for this, like if there is this, and it says, it even gives you like, one of the things it says is there might be multiple solutions. There might be, so, you know, just right there, that kind of helps you where you're just like, oh, there might be like two paths to get to this point. And then so, I guess the first thing that I do, or would do with this problem, let's redraw it. So we have a box, and this is point A, this is point B. You know, I mean, what's a logical way to go that's symmetric? You know, that's kind of the first thing I was thinking, is just like, okay, I'm going to go from here to here, and then I'm going to go at this angle down to here. And then I guess I'll just get to one of the concepts I was talking about with my brother. I was just like, well, is there, you know, it's like there's probably not a place where you would take a curved path, and I don't know how that came up. I don't know if I thought that would be a better way to go. But we just talked about how, like, let's say I'm trying to get from here to here. We're going to call that point C. And I take some sort of curved path. Okay, so cool. I took a curved path. But isn't there a shorter way than taking this curved path? Hell yeah. And it's going to be a straight line. But then with this problem is, like, because you got two different surfaces, you might not be, you know, if you take this angle down here, then you might take a different angle, you know, so let's say you come all the way down to this point, maybe point D, and then you go over. And maybe that's going to be the best way to go. Alright, so one thing that just kind of popped up into my head was just like, well, just because drawing this, I was just like, if I go to here and then go to here, it seems like if I was holding, oh, never mind. Alright, so now I'm just going to get to one of the solutions that I thought of, and I thought this was interesting. And I get how, well, from my perspective, from statics, we learn that, hey, if this is the origin and this is point A, and I have an X and a Y coordinate system, that to get to A I can walk out in the X and then I can walk in the Y. So let's say this is just a unit triangle, 30 degrees, so I'm going to walk the square root of 3 divided by 2, or 0.866 units this way, and then up 1/2, or 0.5 units that way to get to point A. Now, if I do that, if I do the square root of, if I go 0.866 and then 0.5, well, now I'm going to be going 1.36, you know, so my distance if I go here to here is going to be greater than just, you know, having a path this direction. And so that was the first thing that came to my mind with this problem. I was just like, well, what is the absolute shortest distance? I think even that, you know, it's like I don't think someone's mind would go there because you have a box and you just know you can't go through the box. But if this is point A and this is point B, the shortest distance would be going through the box just headed towards B. You have no curves or anything. So then here's where I came up with my intuitive solution. And we're going to do my intuitive solution that I still can't prove. It's going to be this little diagram. And then just probably the actual answer. But like I said, I just got to the aha moment, and then I'll continue on making a more slick video. But here was my more impressive problem solving. Is I said that if this is the shortest distance from point A to point B, and I start out at point A, I know I have to go in a so even like coming back to this 2D, if if I could take a sidewalk from point O to point A, but I can't. It's all blocked off, and so I have to take a different path. So now this one, if I just go along this path is going to be better than walking along this path. And this also comes up in statics a lot, because you could walk along that path, cool, but to get to point A, then you just have to go farther this way. You know what I mean? A distance vector this way added to this way still gets you to point A, but you just have to go farther. I mean, you could travel as far as you want, you know, make your hike hella, and then still have to come back. You still get to point A, but you're going the wrong direction. So then, obviously, if I could, you know, go in here and then up to point A, that would be shorter. But let's say I can't. Let's say I'm just bounded to here, and so that's going to be, that's going to start explaining what I'm going to explain right here. So I have like 3 different surfaces to go along. I could go along this surface, or the back surface. And I still haven't proved this, or, you know what I mean, like from a model, but I want to make a paper cube. It's actually difficult to set up. You'd almost want a 3D printer. Because for this one, all right, let's get to it. So I guess the whole point would be I have to move not in the direction, like, so I'm going to, what phrases should I use? So there's the direct path from A to B. I cannot walk the direct path from A to B. I have to walk like I have to get away from this distance. At any point, let's say I take a step this way, I'm going to be a particular distance perpendicular to the fastest place. And alright, hell yeah. So now I can put it into words. So if I'm right here, or let's just say this is the prime path to walk. I'm going to walk that way, and that also is just the best way to go. If I'm at this point, then I can have a horizontal line from the direct, you know, the fastest, so from A to B, and then this is going to be the radius of a circle. And this circle, if there is 2 paths, will probably go through this face. And then it may or may not go through that other face on the other side. If this circle goes outside that other face, then hell no, these aren't the fastest, because I can get to the same distance, the same projected distance along AB. Like, technically, if I'm right here, I'm basically right here. So whatever path that I'm following, there's this idea, like definitely the idea of cosine. If this is my angle, the sun is shining, this is the sine component. So if anywhere we would do like a perpendicular line to whatever path I'm taking, but then you have the cosine component, which is actually just your, and in this case that represents your distance towards B. It doesn't matter how far away you're getting. You know, in this case, if this is the halfway point between O and A, I get to the halfway point right here. But then I just take a hell of an inefficient route for that second part of that journey. So even just right there really shows that, whoa, okay, you got halfway actually pretty fast. But then, you know, taking a path like this, you are really slow, you know, going from the halfway point to get to A. All right, so let's, so now we have this idea that like if I'm over here, also you can think of it as like shining a light. Like if this is, and then the cosine component's the shadow. So it's like, hey, I got to there. If I'm out here, or let's say here, yep, I got to there, and I still have to get to point B. Cool, so let's explain why if I got to here and then I drew a circle, so this point is on this face. And then I would have a radius to the direct line. I don't know what I'm going to call this. You know, the shortest distance, the direct line. And then I'm going to, you know, draw that circle out. And in this case, it'll probably hit this side. And for whatever reason, it just won't hit the other side. Or maybe it does. Maybe you can go 3 different... oh, Oh yeah, no, you probably can. It probably will hit the other face identically, because I'm still just speculating of what it's going to do. And then yeah, let's come up to here, because here I have took the cube and then made point A and B on top of each other. So I'm looking at a top-down view. My eyeball is looking this way, and I'm looking through point A to point B, and these angles are 120. And so in this scenario, I got to like this point right here. So let's just say that's yeah, and I'm not trying to go a 45. I know that's not the fastest way. So I'm not trying to go to here and then the other direction. So my path is kind of this way. So let's say I just get to that point right there. So here is from there to there, that's going to be the radius of the circle, and it's basically going to be right there. And it's going to probably hit all three faces. I'm assuming it's going to hit all three faces. Oh, okay, so I throw in the towel. So this is where I just thought there was going to be two different directions you can go, but obviously that's not true, because you could start off down this face, or the other face. So now from this problem-solving technique, I know there's going to be three solutions. And I confused myself, but no, this is good, because I still like this video, because it shows one of the difficult things of holding an idea in your head and then like kind of adding to it, or like, you know, having an idea in your head and then because I don't know, I wonder if people are visualizers, but you know, I can visualize a picture in my head. I don't know if everyone can do that. Maybe they have to like write it down first, where I consider that part of math and physics the juggling. You know, I mean, how many ideas can you juggle in your head? Can you even visualize a cube and then in your head visualize, you know, a line going from A to B, and then you could visualize, you know, walk. So yeah, it's just fascinating, because this is why I'm sharing this video, because this came up at the dinner table, and it was just like, hell yeah. The holiday dinner table, I guess, Christmas dinner. And then, yeah, it was just kind of a cool one, because I've never done this one before, but my style is like, hey, like I don't want to know the answer, but maybe I can come up with a different way to solve it, and this does. It says that, oh, yeah, and so let's get a cleaner sheet. So if this is from point A to point B, and what's an inefficient way to go? So let's say an inefficient way to go is down here and then over. Or I'm sorry, like down to all the way to here, over to there, and then maybe to there. That's going to be a horrible inefficient way. We think the efficient way is going to be maybe like here to there. I don't know, maybe that is the efficient way. So again, this really shows the cosine. So if I do get to here, the cosine perspective is just, hey, draw a perpendicular line from the direct line from A to B. And you can see that our forward progress from A to B is just to right to there. And that's going to be the same as walking from here to here. Let's say I just got to there. I made the same forward progress to A to B. And both of these points are still on this face. And so... but this, if I say I'm at this point, it's going to have a larger radius. I could sweep out a larger circle, and yeah, so this is interesting, because yeah, and now I know that this circle will hit three different locations: one on this face, one on that face, and one on the other face, wherever that would be. And then I also know that this point right here is going to hit three locations. One on this face, one on that face, one on this face. So now my solution is that whatever... Oh, this is so hard to put into words. But let's say I chose right here to be my fastest. And let's say there was another yeah. This one is so hard to model, but the other way to model it or think about it is like, hey, I have a line from A to B, and then I just have a bunch of discs, and they're all, you know, let's say I just have a disc that goes through this line at any given point, and then it has like it's like a ruler, so it shows you how far away, and so from here, this circle is going to go through a bunch of different points, but one of them is going to be the shortest radius. So that explains my solution in words, is that if you are on the shortest distance from A to B, there is no other, you can't move in any other direction perpendicular. Ah, damn it, how do I say that? Yeah, so it would be kind of, oh man, yeah, you would have topo lines, and it would be fascinating to do this, because I don't know exactly what it would look like if you would have, okay, so I think what I'm trying to say here is a little bit too complicated for me, but how I got to my solution mentally, I didn't even do, I'm just brainstorming further along this problem, because I know this one would be hard to model. It would be hard to make a paper cube and then chop it perpendicular to this axis and then see what your radius, what the shortest radius would be at that point. But that's, like anything from this surface, you don't need to solve for that. So, oh man, I want to draw another. Oh, sweet. So we have these little cards. So, probably last drawing. I still like this video because it really shows you, like, the brainstorming process sucks. Like, it's juggling. You know, you have an idea and you just have to kind of add to it and then get used to it. And you might be totally wrong, and then you're just making an impression that's, you know, sometimes you're making ruts in your logic that are wrong, and that's obviously the worst. But, you know, nothing ventured, nothing gained. Okay, so we have the direct line from A to B. So, and this is so weird because I wanted to explain for probably the last 20 minutes. I mean, the aha moment was this. It was, I know that I'm going to have to take so I know that, no, I said it, so if I had to do it in 3 steps, I said what I would do is I would get a cube, and then first just measure from here to there, and then measure from there to there. And then I would start to move down this line to like this point. And then I would make a line from there, measure that one, and then that one. And if these two distances were shorter, I would know right then that this is not the fastest, and therefore the answer is going to be somewhere in between. The answer is going to go, the shortest distance has to go through this line. So that was my logic. And that's pretty easy just from a geometric perspective. I don't know how I could prove that mathematically, but I'm sure it'd be fairly easy to set up a scenario where you could just show at least one solution where if you go through this line, that's not this point, from here to there, that's going to be a shorter distance. Cool, so that's the setup. So now I know from my perspective of drawing circles through this, is that if I'm at any point along this line, I can draw a perpendicular line towards the shortest distance A to B. And that's going to be the radius of that circle. So if I'm out at here, this distance all the way to there, that radius. And I think this radius is, so it's really difficult with a 2D drawing, trying to represent 3D, because this radius is the same as that. These two R's are going to be the same. But now I know there's going to be a point on here where I'm going to get the shortest radius. So that's it. That's the solution. At whatever point generates the shortest radius to that center is going to be where you have to go. And so that is that was my proof. And it's just interesting how it takes me like, because I wanted to kind of add on to it, and I'm glad I did, because what I learned is every radius is going to hit 3 points. There's going to be 3 solutions, which I just thought there was 2. Just because I thought the other face was, you know, wonky or something. Just because honestly, just because the way you draw cubes, it just, I don't know, it just seems like going the other. Anyway, so now I'm going to go over the actual solution that's kind of related, but then this made sense to me. So let's see, I'm going to draw this cube. Okay, we have this cube, and what on this one? Yeah, this was a lot better. This was going to be my A. This was going to be my B. And if I just took this distance right here, from A to this point C, and then to B, what I noticed, and then I said, well, you know, maybe there's probably going to be a shorter. They're going to call this D. So if I go here to here, I say, what happens when I do that? And just from this picture, I had the aha moment that it was just like, oh, this angle, you know, A to C and C to B, the angle between those is kind of hard to see, is going to be steeper. So like A to C to B is going to be a steeper angle than A to D to B. So I'm going to have A to D to B. So this is AC to B, and this is going to be AD to B. And because I have a wider angle, I'm basically taking a straighter line. So back to, you know, trying to get from point A to B, this angle is a 90, but if I'm able to go here and then here, heck yeah, my angle is going to be less. And then the opposite is true. If I have to go out to here to this point and then go, my angle is going to be less than 90. Greater than 90, going to be a shorter line. Less than 90 is going to be better. And it still works because let's say I even go along this path. Well, oh, I was gonna mess up, but as long as my junction is in between this triangle, then this is going to be shorter than a point outside that triangle. Now, if you go out this direction, sure, you can still get a 90, and maybe this is obviously this is going to be a shorter distance. But if that's the case, if this is your 90 degrees, you know what I mean? Then if I go farther and then I make the angle more acute, less than 90, I had to travel a farther distance. If I'm inside, I travel a shorter distance. Greater than 90, do a shorter distance. And so that's what we find. Okay, so yep, and I'm wondering if it's probably pretty easy to set up the geometry. But that's it. This video is just about problem solving, and I'm glad it's a struggle because I don't know anything. I don't know. It's the reality of especially doing a riddle where you don't have a base or a textbook saying like, here's the principles that we're using, and you're just kind of from scratch using your general knowledge. But yeah, that was the one that I saw. It's just like, hey, from here to here, it's a sharper angle, and then so there's a point over here that actually widens that angle, and then again. So that one. So right here, here's the sharpest angle, but if I go this direction and then this direction, that's the same thing. It's the same angle as this angle. So then it shows that in between, there's going to be a perfect spot where the angle is less. And then, oh, so that proves, doesn't this prove right here that it's going to be the halfway point? So yeah, so I'm glad I'm slow rolling this problem because there's just a lot of little things that could be intuitive, and I think that's one. If I can identify that this is a sharp angle and it goes to that point, and this is a sharp angle that goes through that point, and I could have 2 solutions. So that I can't rule that out, and that would be fascinating. because let's say the half, yeah, so I have to check that. And one way to check it is just, I love doing this all the time. And so I don't know if I want to make this video any longer because I really don't want to run the numbers. But now what I would do is I would, so I have these two paths. Oh, did I mess it up already? Alright, so here's A, here is B. I can do this 45 and then along this line. Or I can go along this line and then the 45. Both of those two paths will be the same distance. So now the scenario was like I can't assure that the halfway point is the shortest distance. Well, I don't. It seems like it would be. I don't know why it wouldn't be, but I have no idea. Maybe on this side just a little bit, and on this side a little bit. That is the shortest angle for whatever reason. So even just drawing this in, could I see how? Is there any reason? So now, no, okay. So now I can actually say if this is A and this is B, and then I come up to a high point. This is a high angle, and so even if I'm totally symmetric, which am I going to be symmetric here? That's the question. If I hit this at the halfway point, then I am symmetric. But if this is higher on this one, then this is lower. So yes, so that's fascinating. Right here is we have totally symmetric, but if I move this point just slightly to one side, this side is going to be longer, and then this side is going to be shorter. Alright, so a couple things going on here is if I have to get to this ceiling, going to the center is going to be the shortest distance from there to there, compared to it. The way to do this is like, hey, if this is the center and all I have to do is go to there, that's going to be a shorter distance than coming straight up and then over. Is that I don't even know if that's true though. Is that true? Okay, so now I'm just getting into a realm of like just, you know, getting more and more questions. But if one of these gets shorter, like one of them would get shorter, one of them get longer, but then hopefully this radius, you know, if we take the direct line from A to B, this radius would be smaller. But I can't visualize it and I can't prove it. So I don't know if it's going to be right in the middle or just offset a little ways. I can't tell. So so there you go. So this is where I would throw in, you know, an example that just goes through the middle and then just offset it just by a little bit, and then run those. You just run those two numbers and then see if one is, you know, even run it through the center and then just run it just up, you know, just by a 0.001. Let's say this whole thing is going to be like 1 inch by 1 inch cube, and then so the halfway, this distance is going to be 0.5, and then just make this distance just 0.501 inches. Run that in your calculator, you're going to get a difference. You're going to get maybe a longer distance or a shorter distance. That's one way. If you don't know the differentiation, that's one way to do it. Just kind of make a change and see what it does. Does it give you a longer distance, shorter distance? So cool. So I'm done with this video, and I'm done with the analytics. But I just thought this was cool because you could do this. I don't know how you're going to model it. That's the only thing. It's very difficult to take a cube, visually put like something down the center between point A and B, and then put radial discs that protrude through the actual shape, so then you can see what distance is going to be the shortest radius. But if you did that, that shortest radius is going to be along. So if it is the halfway point, the shortest radius is always going to be along this line. There's no any line that's to the left or right is going to be a larger radius to that point. So definitionally, this whole path, this shortest path, every point on here is going to be, you know, perpendicular. If you moved perpendicular to this line, so that needs to be said. If I say this is the shortest distance, but you're just like, well, what if I was just at a point just perpendicular, just high, you know, or yeah, perpendicular to that. Yeah, if this is a line, there is a perpendicular, and we're on a surface. And if I just move just a slightly this way, am I going to be a shorter radius to that center line AB? And the answer would be no. You weren't, because that's the definition of this shortest path. Okay, hell yeah. So I'm done. That was brutal. But no, I really like doing this because it shows you the problem solving. And I feel like I didn't even give anything away. You still have to figure out from the math perspective, you know, go figure that out from the math perspective. You know what I mean? I got to this picture. That doesn't really give you much. But it gives you... Yeah, so I think a video like this is no spoilers, especially if you want to solve this riddle for yourself. And now I'm just rambling, so I got to finish up. But I like the idea of having a concept in your mind that you're just like, oh yeah, like no duh. Like I had this concept in my mind in like 2 seconds. Be like, oh, perfect. Yeah, there's a shortest distance A and B. And as I walk along this surface, I better not be getting farther away, because if there's a part on this surface that's closer to this line, then hell yeah, that's going to be the shortest distance. And then the second thing, you know, to recap, is that I know I ain't taking a curved path, and I know I ain't going to go through that point and that point, so I am going to go through a point here. So whatever point I go through there, it's going to be a straight line there and a straight line there. And then so I know that all I have to do, if I modeled this, is find all the radiuses from this point, going perpendicular to that, and then measuring that radius, and then finding all those numbers, and then and then figuring out what number is the closest. And it could be cool, because it could be like an x squared, you know, something. I mean, we're dealing with triangles, right triangles, so hell yeah, they have this, you know, a squared plus b squared is equal to c squared. So cool. So that might help me more be looking out and excited for the solution could be up and below, and you could have 1, 2 paths along a surface. You could have 6 solutions. So I'm going to say there's either 3 solutions or 6 solutions, but there hella isn't more than that. But yeah, hopefully there is 6 solutions. I will be very impressed if there's 6. And I was going to say something about differentiation. Yes, because if I model it, if I get an equation for the radius for all points along this line, or whatever, you know, if I'm saying this is 0 to 1, you know, on an axis, and then I have an equation for all radiuses from 0 to 1, I'm going to find that the radius, so 0 to 1, and this is radius. It's oh, this is super cool. Great way to end the video, because it's all so good to get something graphically. So if I'm going to say, hey, this is my distance, 0 to 1, and then I want an equation for the radius. I know if I'm at 0 or at 1, the radius is hella. I mean, it's not visually hella, but we know that's going to be the max. So that's going to be my max right here. And then, yeah, so, and then I'm going to have this. I'm going to have... Oh, I think this, so now I'm saying, like, wouldn't it be logical that I would just have a graph that looked like that? Alright, hell yeah. So now I'm going to potentially, so now even like right now I'm in the camp that there's only one solution that's halfway. I don't think being just above or below is going to be any better, because to make that you would have to have a weird graph. You would have to have, the graph would... because right here, this is my lowest point. This is going to be my minimal radius. and still I have like a, something that looks like an x squared, but that's not what I was getting at. I was thinking, yeah, I don't know what I was thinking. I mean, no, but yeah, to get what I was saying, I would have to have a point right here and here, off center of the center, to have a lower point. And so the only way to do that would be weird. I would have to come down here, hit this point, and then go up, and then down again, and then up. But if that's the shape of the graph, I would be super excited, because I don't know, I've never done one of those. You know what I mean? So, but I'm not getting my hopes up that this is the equation for that. But that's one, I know that this is a polynomial that could potentially exist, you know what I mean? Anything that does anything, as long as it doesn't overlap, I think you can express with a polynomial. I think that's a true statement. It can, as long as you can make whatever mountains and peaks and valleys, as long as you're not like going back on itself, you could have an equation for that. Maybe not. Maybe that's not true at all. Anyway, so I'm going to say it's probably unlikely, but I'm looking forward to the 6 solutions. I'm just going to say it goes through the center point, and I've done my analysis on this video. But that's it. I just really like the brainstorming, and hopefully I make more brainstorming videos. And I get how they can be helpful. Because one of the commenters just like, yeah, if I slow roll a problem and go over the brainstorming, it allows your brain to think. And you might have these aha moments. And I think the best thing is to have, like, even for me, is to have an aha moment that's wrong. To be like, oh, I think this. But you're just, oh, no, that's a wrong statement. But it seemed like it could work. Like, I get that a lot. And so I think a lot of brainstorming is seeing, like, that's not a rut, but it can be a rut. It can be like a fundamental that you're just like, oh, I think that if I have a triangle, that A plus B is equal to C. You know what I mean? If you think that, then that's a rut. Or one that came up today that isn't so obvious. If I have a triangle, a 30-degree triangle, or just a 2, 1, and then whatever the hell that is. You know what I mean? Your hypotenuse. If I do this, 2 plus 2, 1 plus 2, and hypotenuse plus 2. Do I get the same shaped triangle, just like bigger? Hell no. You know what I mean? But if I take this 2, 1 hypotenuse triangle and then just multiply by 2 each side, then hell yeah, I get the same shaped triangle. So that's a fundamental that you could go wrong, because I do that in math all the time. There's so many things where you're just like, well, can't I just, you know what I mean? Yeah, that comes up a lot. Anyway, yeah, getting your fundamentals crossed, especially with addition operations, subtraction, addition operations, and multiplication, division operations. Cool. Okay, that's it. I'm going to end this video. Thanks for joining me. Video on problem solving. Hell yeah.